Okay. Hello, everyone. So my name is Haoyi. This talk is about a deep dive into the mill Scala build tool. So about myself, I've been using Scala for about 10 years now. I currently work on Databricks developer platform. Databricks is a big Scala shop. Everything at Databricks is Scala. And I'm the author of a lot of open source projects and book hands-on Scala programming. So to start off, why should anyone care about the mill build tool? So there are plenty of other build tools on the market, right? There's SBT, there's Gradle, there's Maven, there's Pants, there's Pants 2, there's Bug, there's all sorts of other build tools. So why do you care about mill? And for someone who may know nothing about mill, perhaps the best proof is kind of social. So people like mill. Now, the people often will complain about Gradle or SBT, blah, but the feedback from people using mill is largely positive. And maybe the last line down here is worth highlighting. So the task model seems just right. So that's something that is hard. It's not something that you can do that's optimized until it's super fast or super efficient or super scalable. But there's something people find intuitive about the mill build tool. And this is what we'll try to investigate as part of this presentation. So we'll have 4 sections. First, we'll discuss why build tools are hard. We'll dip our toes into the getting started experience with mill. You'll dive into mill fundamentals to see what the real components of mill are all about. And we'll use this as a basis to discuss why mill, why do people like mill, what's so just right about the task model that people seem to find intuitive and understandable. So first, why are build tools hard? So build pipelines and functional programming have a lot in common. So this is from an earlier talk. But consider this like pseudocode. It's functional pseudocode for making a cake or tiramisu. It's Python pseudocode, but it's straightforward. The function at the top takes arguments. These arguments are transformed through a bunch of transformations, passed through and transformed. No real side effects. Each step explicitly lists out the input as parameters, takes only output as a return value. And then you have the final result to return. So no mutability, no global side effects, no local side effects, no spooky action at distance. This is, at a glance, what functional programming is all about. It's about having explicit dependencies and passing data throughout your program. So if you rearrange this code a bit, let's say I'm just going to inline all the intermediate values, so I don't need to zigzag back and forth across the page. I draw a graph to indicate the data flow. So here's the data flow graph. It's a bit spirally. And you find this graph is almost identical to a graph represented by the so-called pipeline view of the same tiramisu recipe. So the structure of the build pipeline is at its core identical to a structure of a pure functional program. So you have explicit dependencies between computations. You have side effects. So just because I built that library doesn't mean that this library gets built accidentally, or just because I built this tool doesn't mean this thing gets deleted. Only no side effects, no spooky action at distance. And the build graph matches the data flow graph the same way that the call graph of a pure functional program will match the data flow graph. In the end, you're still just passing data throughout your program in a well-defined, structured graph manner. So if you want to have some ways for users to specify a build pipeline, like, oh, here's the source code, I want to transform by compiling it, I want to combine the compiled output with the resource folder to create the assembly, I want to take the assembly and deploy it to Maven Central. These also form a graph. And if you want to write the build tool, it's quite obvious that it should be some kind of pure functional program. Like you're defining how you're passing things throughout your build until you have a result that you can return at the end for the user. So if that's the case, then why are build tools such a mess? Like, why do people say that SBT or Bazel or Gradle or Make or CMake or AutoMake and AutoConf and all those other things are confusing? Why aren't all these tools just written in Haskell or Scheme, MIT Scheme? That's pure functional. So it turns out that apart from managing a data flow graph, build tools have a lot of things that most pure functional programs can ignore. So some things the build graph may help with, for example, what the task depends on what needs to run in what order. Well, you can use a build graph to infer that. But other things the build graph doesn't help at all, like how does caching work, disk caching, in-memory caching, how do you run tasks from the CLI, where are things cached on disk? Your disk is not a graph, your disk is a tree structure or hierarchy. How do I define my own custom tasks? Do I write them in Bash, write them in Python, some other language, some weird groovy DSL? So while naive pure functions are very easy and very simple, they don't have all the things that a build tool needs to care about, and build tools need more. And one thing to note here is that each bullet point of what a build tool needs to care about is a whole chapter worth of documentation, tens of pages, maybe 20 pages, to learn about how SBT scope delegation works so you know what task depends on what. Or another 20 pages to learn how SBT paths and globs work, because you're not going to use SBT paths and globs anywhere else in your programming job except for SBT. So here, if you Google the various titles here, you can see for yourself how deep each facet of the build tool experience can be. And unless we find some shortcut, it seems inevitable that any build tool, if you want to learn to use it properly rather than just copy-pasting cargo culting, you'll need to read 10, 15, 20 chapters of documentation to really understand how to use them, what's going on. So that's basically you have to read the whole book just so you can use a build tool. And that's why build tools are hard. So I know lots of people complain SBT has not enough documentation. Lots of people complain SBT has too much documentation. The same complaints apply to Bazel and other things if you've used those. And how is that? How can I have too much and too little documentation? And the answer is, these tools require so much documentation that you never have enough of it, but also just reading all documentation you need to read is too much. So that's why these problems exist. So that's why build tools are hard. So while naively they may look simple, you're just mangling some files, you have some kind of data flow graph. In reality, you have a lot of things that you need to manage. And if you're not done carefully, you end up having to read a 400-page book worth of docs in order to figure out how do I do everything I need to do in the build tool. So for now, let's go into what Mill is like to use. We'll come back and revisit the whole build tools are hard thing later. So let's see what it's like using Mill getting started with Scala. So we'll cover 3 examples here: a single Scala module, some custom tasks, and a multi-module project. So here's a basic Mill build for a single Scala module. It has Scala 2.11. It has 2 third-party dependencies. There's a test suite over here. Has a test framework as a dependency. It extends the Scala module. It's because it's for compiling Scala. And root module just says it's at the root of the repository, so it's not within like a full subfolder, which would be the default in Mill. So the source code, since it's a root module, will live in the source folder at the root of the repository. And maybe we have this foo.scala file that uses a third-party library to just like print some stuff. Not so interesting. So Mill lets you run things like Mill resolve with a wildcard to say, hey, tell me all the things you can do available here in this repository. You can use Mill inspect to say, hey, where does the compile task come from? Let's have a compile task. So it comes from this line. Here's the documentation, Scala doc. Here are the inputs for this. And you can go and inspect any of these inputs to learn more about them and crawl the build graph that way. You run Mill compile, it compiles it. You can run it, Mill run, pass in the command line flags we saw earlier defined in the Scala code. It prints out this thing. You can run Mill test to run the test suite that we have defined below. And I'm not going to show the test code. We can use the Mill assembly. Use Mill show to see the metadata prints out. For example, where did they put the assembly? Well, it's right here. And you can use java-jar or just directly run the assembly. So this is something that you can't do in SBT without a whole bunch of plugins and other third-party tools. You can't make assemblies, a bunch of configuration. Mill kind of makes the easy path easy, so you can do all the things you want to do more or less by default, at least for simple projects, even if we can't give that guarantee for larger projects. And I haven't shown it here, but Mill can also publish to Maven Central by default. No futzing with plugins, this plugin, that plugin, PGP, sonatype release, blah. Tries to provide what you want out of the box. And while this build isn't trivial, it hopefully gives you some idea of what a Mill build looks like. You have some objects, you have defs, the defs have values, you have traits, and that's all you need to do to define a Mill build. So that's like a really simple example. Let's look at a slightly more complex example. We're going to customize this Mill build to do something that's never been done before, that's not prepackaged in Mill and not in any third-party plugins. So first, I'm going to strip down the previous example. I delete the test suite because who needs tests? Remove the third-party dependencies. Just make a really small, simple, really minimal Mill example. I have an object that extends Scala module, and because Scala, I define a Scala version. So that's a really minimal Scala module in Mill. So starting from that, I could define a new line count task. So here I say define line count equals t. So this t thing you may not know about, but just roll with it. All source files comes from Scala module. I'll talk more about that later. I take all source files. I OS read lines, the path, get the size, sum them up. Here's the line count. And you don't know what all source files is? Well, you ask IntelliJ, and IntelliJ will happily tell you. All source files comes from here. It's of type T of sequence of pathref. It has a Scala doc. All individual sources for the Scala compiler comes from this jar. So even though you may not be familiar with all this, when you actually do it in the IDE really guides you along and can help you, just like it helps with any other Scala application. And so, again, we're just using normal Scala to do map, sum, OS read lines. You may use OSLib in your other Scala toolkit or your other projects. This is all just vanilla Scala here. So we haven't used line count, but we can use show to show the metadata. Line count returns an integer, so the metadata is just an integer. In this case, it's 19 lines long. Use the build inspect. I didn't include any Scala doc, but you can see where in the build.sc file it came from. We captured that during compilation. You can see what inputs are. Inputs all source files. And if you want to use line count, here's an example where I take the resources of the module. Again, resources, you can use the IDE to find it if you're not familiar. I override it. I write line count.txt to the destination folder as the line count as a string, and I just return that destination folder with that one resource file in it. So now with that, I can, let's say I put in this foo.scala file that just reads the resources from the resource path and prints it out. I can use mill run, and it will fish it out at runtime. It'll take the sources, sum them up, count how many lines there are, put them in the resource folder, and when you run the code, it'll compile it, fish it out at runtime, and read it and print it out for you. So, well, this is a kind of a toy example. It shows how easy it is to customize mill to do the kinds of custom logic common in real-world projects. Maybe you need to scrape your source code for strings for internationalization purposes. Maybe you need to include a resource file with all the your third-party dependencies as a manifest or bill of materials. There are all sorts of things that you may need to do that are special, and chances are everyone has a different projects, and every project needs to do different things because that's what your business needs. And mill makes it very easy for you to just do the thing that is different while still doing it in a principled manner. So over here, you can't really see, but line count over here is incremental. You run line count twice, it won't double count your files. When you edit your files, it will then count it again. It's paralyzable, so line count and compilation can happen in parallel. You already saw it's introspectable. If line count is some big build file, thousands of lines long, you can ask, hey, inspect this, where did this come from? What's a Scala doc? And it will tell you. So mill doesn't just let you write hacky ad hoc code. It actually helps you with guiding you to make that code functional, doing things by returning values rather than by writing randomly to the file system. And also gives you the support necessary to introspect and manage it, parallelize it, and make it easy to use. All the things you normally want in any build tool. So yeah, line count and resources, as I said, you could parallelize them and they would run like this. In this case, line count is really small, so it doesn't matter. But in a bigger project, you may be doing more interesting things, aspect J bytecode weaving or something. These can take a significant amount of time, and you don't want to rerun them unnecessarily. Yeah, so we already saw all of this. You can inspect it, you can ID support, all that. Okay, so that's how you customize a mill module. Just write a def, override defs, return things, and you're done. It's basically simple, pure functions, but with some object-oriented traits, overrides, and stuff mixed into it. So let's look at an example of multiple Scala modules. So this example build contains two Scala modules. There's object foo extends my module, object bar extends my module. You can see my module extends Scala module. That does what you expect. There's a shared Scala version between them. You can put other shared things in the shared trait. And you can put the things that are not shared in the individual objects. For example, they have different sets of third-party dependencies. And in this case, foo, the object foo has a module dependency on the object bar. So again, this is pretty vanilla Scala code. None of you should be too confused about this, I think. And this ends up requiring this project layout. So neither of these are root module. I kind of touched on that earlier. Since they're not root modules, foo, all this stuff is in the foo subfolder. Foo/source, foo/resources. Same with bar. The output goes in the out folder, similarly under the path. So out/foo, out/bar. There's a JSON for your metadata output. There's a destination folder if you want to read and write files, whether to return them or just as a scratch space. And you can use wildcards like _run, just list out all of them, compile all of them. You can run individual things, mill foo.run, pass in flags. I didn't show you the code, but just roll with it, prints things out. And you can use brace expansion to run multiple tasks at once. So you can say mill show foo bar.assembly. It'll expand to foo.assembly, bar.assembly, run all of them, show you the output assembly paths. Nice format, nicely formatted JSON. You can easily pipe to downstream tools or parse with other applications. So that's for setting up multiple Scala modules. So this is, so far, this has been a really quick tour of what it's like getting started. You have a small module, you have a test suite, you have 2 modules, you want to customize something a bit, have a custom resource. And hopefully it kind of shows what it's like getting started with Mill. It's not complicated, and it's pretty straightforward Scala code. So far, we've been relying a lot on this Scala module trait. So the Scala module trait comes with a whole bunch of built-in helpers for all the things you want to do in the Scala module, like compile, test, run, assembly, publish, all sorts of things. And we've been relying on that a lot so that we barely have to write anything in order to make our build work. So that's great for getting started. And it's kind of the same experience in any other build tool, like Maven or SBT. You just put in the plugin and it works, great. Until one day it doesn't work. And then what happens? And you really need to dig in and understand, like, okay, this plugin did something wrong. Why is SBT doing this? Why is Maven doing this? What are the scopes? What are the phases? What's the actual data model when you're not just cargo culting? And that's what we're going to go into for the next section of this talk. So let's say we don't have any pre-built scaffolding. There's no Scala module. There's nothing. We're just using pure mill. What can you do with it? So we have 3 parts of this. One, we'll talk about tasks. We'll talk about modules. And we'll combine these together to make our own kind of like DIY module system using Mill that is a kind of a simple version of the Scala module that you saw earlier. The goal of this is that you can get good understanding of how these building blocks work. So when you see a simple mill build or a more complex mill build later, or you need to customize something, you have the tools necessary to do so. So first, let's talk about tasks. So the most important tasks to know about are t.sources. So those are over here. Like, this is a sources task that depends on the source folder. And t targets. So this t without any suffix or means a target that is not a source folder, but something that's computed based on upstream targets. So here, sources depends on the source folder. All sources is a target that we walk the sources path, find all the Java files, and return a reference to them. Line count is a target that returns an integer. You can annotate types like any other Scala code. We print out some logging message, and we take all sources defined up here, read all the paths, and count how many lines, and sum them up over here. So this simple build results in the build graph in the top right. So sources gets used by all sources gets used by line count. And here we have no Scala module, there's nothing, there's no helpers. All the things you see on the left are all the things that exist in this build. So again, we're not using line count anywhere downstream, but we can start using mill show to do things with it. Yeah, and all the normal things will apply, like caching, incrementality, parallelism in a more complex build, and so on. So targets can run arbitrary code. So here we extend our small build graph with 2 more targets, class files, and assembly. So you can see the change to graph is up here. Class files takes all sources, takes all their paths, passes them to Java-C to compile, and returns a reference to the destination folder containing all the compiled output. Assembly takes the class files and calls jar-cfe on it with some main method, main class, and returns a path reference to the output jar. So this is, again, just normal Scala code using OSLib. You can use the same code in any other application. And that's all you need in order to make a Java assembly. So here, the first time we run it, you can see it prints out logging messages, and we use show, so it shows you the name of the assembly you created in JSON string. You run it a second time, it's cached. You didn't make any changes. Why should it do anything? You touch some Java, you touch the source folder, and maybe you create a new Java file, and you run it again, and it decides that, okay, you touched something, I'm going to rerun. All done automatically for you. So there's no logic in here dealing with caching. Mill takes care of that, and you just need to write what you want your build to do. Lastly, this is a full-fledged assembly, so you can take it java-jar, like what you did in Java 101, and pass in some arguments, and it prints out whatever the main method does. Here is not shown. So here's a full code for the worked example. On the left, you can see sources, all sources, and line count. On the right, you see class files and assembly. And so the mill tasks, they are just functions that can contain arbitrary code. You can have logic running in memory, like we do for line count here, using map, sum, whatever. You have logic running in subprocesses, like class files and assembly. They shell out to Java C and jar. And the assumption that mill makes here is that every task has to list out all its inputs. So for example, all sources takes sources.path and does something with it. Line count takes all sources, does something with it. We never just like look for something on disk and grab it out. We take things as using references and as inputs, and we return the value. So all sources returns a list of path references. Line count returns an integer. Class files and assembly returns a path reference to the thing that it computed. So this is very functional programming. Like we're not reading, even though you need to read and write to disk, we're not just anyhow reading and writing and side effecting all over the place and having to worry about some guy accidentally deleted my file and caused my build to fail. Or some guy accidentally created my file, so next time I run my task without running that task unrelated, my task will fail because it didn't have the file created. All this is pretty structured in a functional programming manner, and we control it so that all the tasks, they work with these, like, let's see, they work with these t.destination folders so that each task only reads and writes its own destination folder, and even though you're writing to disk, you're never going to have a side effect that clobbers someone else doing something else. So that's it for tasks. Let's talk about modules. So modules at their simplest are just namespaces that you can put tasks in. Again, this is a very vanilla mill build, so there's no helpers. There's mill.module that imported from mill._, and there's t that imported from mill_, and that's it, nothing else. So here I have foo, there's a target bar, I have foo.quux, so a target foo.quux.baz. These for now just return strings, they're very simple. This results in the following data structure. You have the root module, that's kind of the implicit thing that surrounds all this that's not shown. You have the foo module, you have foo.quux, foo.quux.baz, and foo.bar. Here the dashed lines are the modules, the solid lines are the targets. So here you can see that we can use mill show, like what we saw earlier, to show the metadata that's returned by each target within the module. So foo.bar returns the metadata of, well, foo.bar, foo.bar.quux does the same, foo.quux.baz does the same. And you can see that the output goes directly to disk following the same pattern. So out/foo.bar.json, out/foo/quux/baz.json. So this example is trivial. We're not doing any interesting logic here. But the purpose is to illustrate how Mill's core module data structure works. So you have the modules in code on the left, the logical tree structure on top, you have the CLI on the right, you have the file system layout for the output on the bottom right, and all of these match really closely. So there's no mapping you have to do to realize that, oh, this task in the code is run by this other syntax on the command line that ends up being placed somewhere totally unrelated on disk. They're all mapped really closely so that it's very easy to find things, whether from the CLI or on disk when you're trying to figure out what's going on. Mill modules can be turned to traits for reuse. We saw that earlier. So we had trait mine module, extend Scala module. Here's a very minimal foo module that, again, is a synthetic example, doesn't do much interesting. I have an abstract target bar of type target of string. I have a concrete target quux of type, which is type inferred, and it's a target with the output value of bar plus world. So it is a normal Scala trait. I can instantiate it here. I instantiate with foo1, foo2. They have different concrete implementations, foo1 and foo2. And if foo1 gives you an overrides quux, foo2 gives you implements a new target baz. This results in this module tree. So root foo1 bar, foo1 quux, foo2 bar, foo2 quux, foo2 baz. And you can do all the normal things you expect from the command line. And these should more or less do what you expect. So for example, if I look at, wait, where'd my mouse go? Okay, here it is. So foo1.quux, well, foo1 is here, quux is here, foo1.quux is super.quux uppercase, foo.quux is bar.world, bar is hello, so hello world to uppercase, so hello world. So it's just like normal Scala code, just with these module traits and these T target things that you can generally ignore. So that's more or less what you need to know about tasks and modules. And that's the foundation on which all of MIL is built. So let's see how we can combine these two things to make our own version of Java modules, similar to the Scala modules we saw earlier, but totally from first principles. So it's a bit of code here, so if you can't see at the back, maybe come forward. But I'll walk you through it kind of step by step. First, we have trait DIY Java module extends module, and DIY Java modules, that's our name. We have this module depth string, which can override later to say what my upstream modules are. Our main class I can specify. There's this traverse thing that I'm going to ignore for the time being. So down here is similar to what we saw earlier. We have sources. We have compile, and all sources I just put as part of compile. So all sources takes sources, walks it, calls javac on it, returns it. Class path is new. Assembly is similar to what we saw before. I take the class path things, merge them. I pass them all to jar. I generate out.jar. So there's some differences here. For example, we have this class path thing in order to let us bring in more than just the compile output as a class path. Here we include upstream class path, and upstream class path uses this traverse. It's similar to future traverse in that lets you take a sequence of methods, sequence of modules, in this case, a sequence of DIY Java modules, take all the class paths out, and I generate one big list of one big combined class path. So basically, all my upstream class path, I combine it and I pass it to my own compile method and assembly method down here, here and here. Because now we have multiple class path roots, assembly has to loop over all the class paths and merge them together. That's what this line does. For each class path in the class paths, I copy them into the current destination folder and merge them. And that's more or less it. So apart from these few small changes, this is more or less the same as what we saw earlier. Just put in a module trait, and then we can reuse it and wire them together. So this graph on the right kind of shows what's going on. So we can instantiate it very similar to how we instantiated DIY Java module earlier. So class object foo extends DIY Java module. I define module depths. I have the main class, because object bar extends DIY Java module. Bar is nested within foo. Quux is a sibling of foo with a different main class and a module dependency on foo. So that's all I need. I can run mil show foo.assembly. Let's see down here. It shows you the path of the assembly that was generated. I can run java-jar and generate its, see its output. So this is a final build graph after we've instantiated and wired together the 3 DIY Java modules. So it's the same as the small graph we saw earlier, except now that foo class path and foo class path here and foo compile, they are no longer kind of abstract, pointing at nothing, but they are wired up using to the upstream modules so that foo compile and foo class path depend on foo bar class path, quux compile and quux class path depend on foo class path. So we just templated out 3 copies of this module, wired them together, and we're done. So here's our build graph. So this build graph is incremental. So for example, if I made a change of foo.sources over here in red, and I run quux assembly over here in blue, it will only reevaluate these targets here highlighted in green. It will not evaluate quux main class, even though it depends on foo quux assembly, because quux main class did not depend on the thing that I changed. It will not reevaluate foo.assembly, even though it is downstream of foo.sources, because I'm not running foo.assembly, I'm running quux assembly, and quux assembly does not have foo.assembly as a dependent. Go on, Julian. Yeah, so it's similar to why you need traverse for futures. Like in this case, we have module depths. If I map the class path, then I'll get a list of targets, right? And but in order to use it downstream, I want a target of lists, so I can flatten them later. So it's similar to if you have futures, you're the wrong way around, you have this traverse function to flip them. Yeah. So as over here we said, it's incremental. It's parallelizable. So if you give it 3 threads, you could run foo bar assembly, foo assembly, and maybe portions of this red thing on 3 separate threads. Each color would be 1 thread. You can parallelize it. Mill gives you very nice Chrome profiles. You can load this into your Chrome browser and see exactly where your time is going and who's running a parallel with who's waiting for who is the longest poll, and who is taking all your time. You can inspect anything to see what's going on. Like I can see what all the different class paths are in case I didn't know, and I can do this from the command line without having to add print statements everywhere. I can use mill visualize to give me like subsets of the graph that I'm interested in. So for example, here I say, visualize me all the compile methods, double underscore, which is a wildcard.compile. And it tells me that foo bar compile is used by foo compile, which is used by quartz compile. Like basically simplifying this graph which can be quite complex in a real build, to the portions you really care about and how they relate to each other. And they're reusable. So I templated this out 3 times. You can template it out more. And you can template them out and wire them together, as I showed you earlier. Lastly, they're extensible. Like let's say I want to do something funny. I want to do some aspect J bytecode rewriting somewhere. I want to do some source generation, like with Golang style generics, old ones, using the Aboriginal syntax for the triangle braces. So you can do that. Just override it, do the transformations using normal Scala code, and you're done. Use override and super. So it's worth calling out again. This code here you wrote on the left doesn't have anything to do with parallelization, caching, incrementalization, introspection, or any of those things that you really want, but you don't want to have to think about. This code on the left really only has the business logic you care about in your build. I have sources. I want to walk them and pass them to Java-C. I want the assembly to merge all my class paths and pass them to jar. I want to be able to wire them together somehow, and there's a bit of boilerplate here. But generally, it's nothing to do with, you're not writing to a cache folder and checking for invalidation. You're not saying that, oh, these things must run in the future because they're parallelizable. I want it to be fast. So with mill, you just write the business logic in your build in relatively straightforward, more or less pure functional-ish code. And mill will take care of all the other things that you definitely want, but might not even know you want when you first get started. So like earlier in this talk, we looked at the Scala modules. So Scala modules built in. On the right, you can see these are how we use the DIY Java modules that we just wrote a few minutes ago. And yeah, it's basically the same thing. And that's how the Scala modules in the mill kind of prepackaged libraries are built. You can modify them with the same overrides you do with your own. You can build your own modules completely from scratch. And there's nothing privileged here about the kind of built-in, this is the only thing that mill does. Mill will basically take whatever business logic you want. Maybe you want to render PDFs. Maybe you want to make a static website. Maybe you want to take a bunch of static web content, hash it, put in a tarball, upload it to S3 for a CDN to serve. So you can just throw whatever business logic you want at mill, and mill will automatically do the parallelization, incrementalization, and introspection for you, which is kind of nice. So that's it for the mill fundamentals. So we've talked about why build tools are hard. Looked at the getting started experience, basically filling in some pre-built traits. We look at the mill fundamentals, where we build the traits ourselves and see what it's like to use fundamental building blocks. So the last thing to discuss is, why do people like mill? Like, what's all this about? Why do people think it's a nice build tool? And to me, that comes down to the mill's 2 core concepts. There's a task graph, the module tree, we've covered both of them in the last section, and how they're embedded into the core Scala language. So the first concept is a task graph. On the top left is a task graph that we discussed earlier with our 3 modules templated out. So this graph is captured ahead of time. It's what gives us the ability to parallelize things, introspect things, cache things, and so on. And if we revisit the big list of questions from earlier, and what's hard about build tools, we'll see that the task graph is able to answer the first few of these questions. So what task depends on what? Well, look at who's upstream of you on the task graph. What can be run in parallel and what can't? Well, you depend on each other in the task graph, yes or no. What runs in what order? You do a topological traversal of the task graph, Tarajan's algorithm or something, and you run it in that order. So all this is pretty straightforward and hopefully should be an obvious answer to anyone who's dealing with graphs and evaluating things on them. And it's almost the same thing that if you have a Pascal program writing pure functional code, you evaluate it, it'll call into all the functions, return all the values, and then you get the output out at the end. So this should be straightforward. The second core concept behind mill is the module tree. So consider again the tree we saw earlier. So modules are just objects that send mill.module, but they form a tree that contains targets at their leaves. So the structure of the mill module tree intentionally mirrors the tree structure of your file system. Basically, all your software projects are managed as file systems. You all have Git repos, Mercurial repos, Perforce repos, whatever. They're all a file system on disk. You don't have like a weird graph file system that you use to develop software. No, you have a file system, Linux, Windows, whatever. It's a tree structure with folders and folders within folders. And mill follows that very closely so that the tree we have, where's my mouse? The file system tree we have in the bottom right is identical to the logical tree we have in the top right. And the same applies to the output folder. The output folder mirrors it exactly. So not every build tool makes the same decision. SBT has a 4-dimensional hypermatrix as its main data structure. So here's a visualization of what the 4-dimensional hypercube looks like. SBT is like that, but it's more than 2 things on each edge. It's like this huge hypermatrix with 4 different ways of scoping things and how they interact. And yeah, so most developers are familiar with trees. Maybe fewer developers are familiar working with 4-dimensional hypermatrices. And that's one of the reasons why mill is somewhat more intuitive than SBT, and at least until you all learn to work with tensors in like college. So in addition to just following conventions, like that's always great, mill ends up answering the next few questions using the module tree. So where can tasks read and write to disk? Well, you look at the position of the module tree, look at position of the file system tree. Well, here's your destination folder, .t.dest. Where are they cached? Do the same thing. Here's your JSON file, something.json. How are tasks run from the CLI? Well, the same something.something that you have. You call in code. You use the same thing that you call from the CLI. It all follows a module tree. So, and cross builds we haven't really covered, but they follow the same principle. So you're all already familiar with trees. You're especially familiar with the file system tree. So you look at this, and this should be pretty obvious in how this thing works. Like you have a tree structure, and it follows exactly as you'd expect it to. So the last and final reason that mill works so well is the way it embeds itself into the Scala language. So it's smooth enough that you may not even notice that there's magic going on. Sure, there's this T thing here. There's this module thing here that maybe not used in normal code. But inside of, and there's some parentheses here that you might not expect when calling a zero-argument function. So there is a bit of boilerplate in annotation. But you can throw this at like a new grad and ask them to read this. And so yeah, I take the all source files, I read their lines, I get the size of the line count, and I submit. You look at this one. I write to the destination folder this line count.txt and write the line count as a string, and I return the folder. So this should be pretty straightforward despite the small amount of annotation. So mill uses this embedding to answer the last few of these questions. How do I define my own custom tasks? Def. How do I pass data to each other? Return. Or in Scala, you can leave out the return, just put the last expression. What APIs do tasks use to do things? Like, do you use a special like Gradle file system API or the SBT IO module? No, you use the same APIs used in other programs. Yes, OSLib, you can use requests. If you want to put in cats, you can put in cats and do your own funny things. It's all fine. You want to shell out, you shell out. Shell out to Java-C, shell out to jar. These are all normal things that a normal person does in normal programs. And mill lets you do all of these normal things in your build system as well. So you should already be familiar with how to do this. So it turns out that functional programming, while it's an important part of the build system, it really mirrors the task graph and how you can work with it, is not the only thing that's important. The other things that are important include things like objects, traits for reuse, objects for hierarchies and namespacing. These are all like object-oriented programming 101, and mill makes heavy use of it in order to make itself easy and efficient. The last thing is that mill really embeds itself into a Scala language, so you already know how to do all these things. There's no special syntax for defining a mill task. There's no special syntax for annotating dependencies, and no special syntax for saying that, oh, this runs in parallel and this doesn't. You just write normal Scala, and it more or less just works. So with these just 3 core concepts, we've already answered our entire laundry list of questions on the left that could easily be a book's worth of documentation in how to do in any other build tool. But that's not all. So the seamless embedding into Scala means that the task graph matches the method call graph. So all of you know how call graphs work. I call you, call you, call you. Your IDE can follow them. Your static analysis tools can analyze them. You can visualize them if you have IntelliJ. You know, everyone knows how call graphs work. JavaScript has call graphs. Haskell, C++ all have call graphs. And this task graph is exactly the call graph you see here. Similarly, the module tree matches the object reference graph. And you all already know how object reference graph works. Everyone knows how object reference graphs work. You have objects that refer to each other, can like something dot something dot something dot something to find the object that it leaves. It's a bit more restrictive than object reference graphs. In most programs, it has to be a tree structure. It has to be rooted at one place. You can't have random cycles and other things in your object module tree. But fundamentally, you look at this thing on the bottom right, and you look at this thing on the top right, and it's you'll know how this thing works. It's the same object reference graph you use day to day in any other Scala program. So given that you already know how the call graph, the task graph, call graph works, you know how the object reference graph and module tree more or less work, what's left? So the only thing you need to learn to use MIL is you need to have gone through Programming 101, where you learn about functions that call each other, and you learn about objects that can contain each other. And that's kind of the meat and potatoes of what MIL is all about. Like, sure, there's a lot of detail later. You can tweak the parallelism, you can tweak the caching system, there's some in-memory caching. But the core data structure is stuff that anyone who has done programming before should be familiar with. And that's why MIL doesn't need a 400-page book in order to learn it. You can come in, you can start defining things, calling things, referring to things, returning things, and it just works and does what you expect. And it turns out it's enough for you to build a build tool using this without any special magic. So people talk a lot about things like build tools where, oh, is Scala better than Groovy? Is Groovy better than YAML or TOML or XML or whatever? And all these things are important, but also very superficial. It's like when you look at the Maven POM, for example, a bunch of XML with modules, plugins, like maybe you have the Sonatype plugin, you have the Sonatype staging plugin, Maven assembly plugin. And all that's great until something goes wrong. And then once something goes wrong, or you want to customize something that's not the default behavior, you start having to figure out how Maven answers all these questions in order to do the thing that you want. And this heavy reuse of your programming knowledge is why people like using MIL, and why it's so uniquely intuitive and familiar, even for people who have never seen it before. So to wrap up, in this talk, we did a deep dive into why MIL works as a build tool. We started off looking at why are build tools hard, and looked at how it's like getting started with MIL. You look at how it's like using MIL's fundamental building blocks. And lastly, discuss why MIL can feel so familiar and intuitive to use. So among all the attempts at writing alternate build tools for Scala, there's like a whole zoo of them, right? There's Bloop, there's what C, there's CBT, there's all sorts of different build tools, there's Fury, whatever. MIL's one of the only ones that can actually be used kind of in production. So Scala CLI is using MIL, Corsair is using MIL. There are lots of big projects using MIL. Ammonite has like 100 submodule MIL build. MIL works and has worked for several years and is definitely production ready. But MIL is more than just a better SBT. It's kind of unique even when compared to things like Bazel or Gradle or Pants or Buck, in that it's a build tool that leverages everything you already know about programming, about functional programming, about object-oriented programming, about how to do things in the Scala ecosystem using libraries, and leverages that seamlessly enough so you can get started and it feels seamless when you first start using MIL. You come in with MIL, you learn just about nothing, you don't need to learn anything, and you can immediately start doing things and configuring your build in a way that's functional and principled. And that's what you should take away from this deep dive into a MIL build tool. Yeah, so that's it. Thank you.